Before we move on to our next topic, I want to do two more examples, and to save time, I'm going to do them in parallel. These types of beams, where they're fixed on one end, they have a special name. These are called cantilever beams. Okay, so cantilever beams. I'm going to load one up with a uniform load of W, and the other one I'm going to put a point load on the end. It's sort of like a diving board where someone is standing on the end of a beam, or you're walking a plank on a pirate ship, and the plank has a length L. This distributed load of W has an area of W times L, and it's in the middle, which is at L over 2. In the interest of time, I'm just going to solve for the reactions. This reaction here is W times L, and this moment is going this way is WL squared over 2. It's just WL times the distance L over 2, or WL squared over 2. And on the point load, you have P going down, you have P coming up, and this moment is just the force times the distance, or P times L. Next, we take the cut. I'm just going to cut there, and to make our life easier, I'm going to circle to the right. I don't want to involve those reactions, so I guess I didn't even need to solve for them. Okay, there is no rule written in stone that X has to start at the left and go to the right. And to make my life easier, I'm just going to start at the right and go to the left. You know, a lot of cultures, some cultures, they read from the right to the left, so that's not too bad. Or if this completely bugs you, you could walk around the beam and look at it from the back, and then X will be going from your left to the right. I have trouble with this every time I lecture in class. When I look at you, what's my left is your right. It gets confusing that way. But anyway, to make my life easier, I'm measuring X from the free end, not from the fixed end. Here's everything inside the loop. There we go. That distributed load W over a distance X, and that will have a resultant of the area W times X, and it will be at a distance X over 2. Another reason I wanted to measure X from the right is that the cut will be on the left. And remember that positive V on the left side cut is up, and positive moment is this way, making a smile. And here's the free body diagram for the cantilever with the point load. You have this part of the beam, distance X, with the load P, and on the cut, which is again on the left side, V is positive going up on the left, and there's the M causing the smiley face. Taking sum Fy is 0, up is positive, I get for this one, V is going up minus Wx coming down equals 0, or V equals Wx. For this one, we have V is going up, P is going down, that's it, equals 0, so V equals P. Taking moments about the cut equals 0, counterclockwise positive, we have, let's see, minus M, that M is now going clockwise, taking about the cut, there's no moment due to V. We have minus the resultant Wx times its distance to the cut, which is X over 2 equals 0, and we get that M is minus Wx squared over 2. On this side, we get minus M minus P times X is 0, or M equals minus Px. And in the interest of time, I've gone ahead and drawn the beam the shear diagrams and the moment diagrams for both of these. And here's the answers, and you can make these plots in Excel or however you want. There are other ways or other clues that help you with drawing these plots, and you'll learn all about that in Mechanics of Materials.